Saxon Advanced Mathematics, Lesson 28. It's a two-parter. Both are algebra. The first part is pretty straightforward, and the second part will make your hair stand on end. It's going to be fun. Buckle in. Factorial notation, what does that even mean? I'll show you. This is a new kind of calculation that I don't think we've used before. And the problem looks like this. It says evaluate, and then there's a 5 with an exclamation point. What in the heck is that? That is a factorial, okay? So that's what the exclamation point means. We read it as factorial. This is 5 factorial. What 5 factorial means is you start with the number that's listed, 5, and then you multiply it by every integer until you get down to 1. Okay, so that's what the factorial means, is start with this number and go all the way down to 1. And all we need to do is multiply, right? So this much is 20 and this much is 6. So we can say that 5 factorial equals 120. Is that right? Yes, that's right. Okay, well that's pretty easy. And spoilers, I'll tell you right now, there's a button on your calculator that will do this for you, but we're not going to rely on that for a while. Let's make it a wee bit harder. I can hear you groaning. Why do I always have to make it harder, right? Now we're doing 9 factorial divided by 3 factorial times 5 factorial. It's so fun writing those exclamation points. I hope you enjoy it as much as I do. All right, let's write this out the long way, and then I'll teach you the shortcuts. So this one would go 9, 8, 7, 6, 5, 4, 3, 2, 1, right? And then we're dividing it by 3 factorial, which would be 3 times 2 times 1, times 5 factorial. 5, 4, 3, 2, 1. Okay, so how do we simplify this without losing our minds? What we do is we look here and we take the larger of the 2 factorials that we can reduce against the 9, right? 9 is biggest, 5 is next biggest. So we follow through this list of factors, and later you won't have to write them all out, you can do it in your head. And we can see that this whole list can be canceled out against that whole list. They match, right? And we'd rather do it with the 5, because if we compared the 3 to the 9, we just wouldn't be crossing out as many numbers. We want to cross out as many as possible. So all of those factors are now gone. And we've gotten rid of this 5 altogether. Now, to continue reducing, we just look at these and the remaining factors in the numerator, and we just look for whatever seems to fit the best. And I can see, oh, the 3 and the 2 are going to go against the 6, right? And so now our final answer is 9 times 8 times 7. 9 times 8 is 72. So if we just multiply 72 times 7, we should be good, right? It's 14, and that's 50. So 9 factorial divided by 3 factorial times 5 factorial equals 504. That's our final answer. That's not all that hard, right? Sometimes the numbers get a little crazy. But again, there are buttons on a calculator that will do this. We're not using them now, but I just want you to be aware of that. Ready? Let's do another one. Oh, sure, why not, right? There's just one more of these, I think, right? No, there's 2 more. 28.3. All right. 14 factorial divided by 6 factorial times 11 factorial. Now, I'm going to write some of them out, but not all of them out. I'm going to make this a little bit more efficient. Now, I can see 14 is the biggest number, 11 is the second. So I'm going to cancel the 11 against the 14. Let's look at an easy way to write that. 14 times 13 times 12. Then when I get to 11, I'm just going to write 11 factorial because I don't need to keep writing all those other numbers. I'll just stop at 11 factorial. Does that make sense? Then, when I write the bottom, I'll write the 6 out all the way down. 6 times 5 times 4 times 3 times 2 times 1. Writing the times 1 is kind of silly, but that's okay. Times 11 factorial. Now I can just cancel these two without writing all those numbers out. And then let's see, what else can I do? 3 times 2 is 6. I'll multiply these, I'll divide 6 and the 12, that'll become a 2. All right, I can do this against this, and this will become a 2. And then I can do that against that, and that's a 7. So what am I left with? I've got 7 and 13, 6 and 5. These 3 guys are all prime. There's nothing in common that's not going to work. So my final answer reduces to 7 times 13 over 6 times 5. And that equals, let's see, I can do this in my head. 7 times 10 is 70. 7 times 3 is 21. That's 91 over 30. And that will not reduce. All right, so this is a clever way to minimize how much I write, but still be super intentional on how all these pieces are flying around. And I'm going to show you this one. This one does, John invites you to use a calculator. And my calculator's tied up. I really need to fix that problem. But I'll show you how it works. He says use a calculator, the factorial key on a calculator, to help simplify this answer, to help evaluate. Right? Okay. Well, the calculator works like this. You hit 14 and then the factorial key, and it will give you that value. You could punch this all in, but John's asking you to think about how you might use the factorial key to simplify this. And what I'm going to suggest is, okay, think of this as 11 factorial divided by 7 factorial, because that would work, right? You put 7 factorial next. That would be the next one in the row. And then this could be like that, and then these would cancel, and there would be our original problem left, right? So what you can do is use this as a way to calculate to get you, it'll be the same as this. Does that make sense to you? 11, here, let me write it out longer just so you can see. 11 factorial would be 11 times 10 times 9 times 8. I don't have to say it, you know what I'm writing. Right? And now we're going to divide that by 7 factorial. 7. And now we see that all of this cancels. And it gives us this original problem back. So by changing this into a factorial button, we can use the key and quickly calculate the answer, which is wild. I'm just going to write it again so I can write the values next to it. This equals 39,916,800 over 5,040. That's what you'll get if you use the factorial keys to generate those answers, and then that reduces to 7,920. See if you can get your factorial keys to calculate this for you, and that would be the answer to that, right? Cool. And then we could also check this. We can check the answer by saying, okay, this should be 110 times 72, right? 022 077 7920. And there it is. So by doing this calculation by hand, I can double check that this factorial button gave me the right answer. Okay, enough about factorials. We're going to use them in some calculations later this year, so that will become relevant at that point. Now what we're going to do is we're going to dip our toes back into the water of these rate problems that we've been playing with. They're hard, and now we're going to make them even harder, I'm sorry, because we're going to solve them not with numbers but letters, thus the word abstract. Before we dive in, I want to just give you a little bit of something to think about that we will use. We know that we have thought of these as distance equals rate times time, right? And the last time we did them, we found out that, oh, you could actually multiply rate times time and have it be a job. Or you can even mix it up further and say it's rate times time times the number of workers, right? And you can let that be a job too. All right, so this is crazy spin-offs that we've done from our basic guy. Today we're going to go back to this one. We're not going to talk about these as much. We're going back to this. And what we're going to do is we're just going to solve this equation for time and for the rate so that we can play with the individual pieces of this and we know how to create it. So what I'm going to do to find the time, I'll start with distance equals rate times time, and then I'll divide both sides by r so that t is by himself, right? That's what I'm trying to get. And so I can say that time equals distance over rate, right? I'm just doing simple algebra to isolate each of the three letters. We've got with the D, now we have the T, and then let's do the same thing with the R. Distance equals rate times time, and this time we'll divide away the T, right? And so we get rate equals distance over time. Now, these two equivalent equations are easy enough to do mentally, right? You can just quickly divide away one or the other. But when we get into the heat of some of these problems, it's going to be nice to have this right in front of our faces so that we can quickly refer to any one of these that we want. All right. 28.5. These are all two-step problems where we're going to get some information and we're going to find one piece of information, often it's a rate, and then we're going to use that to solve a second scenario. So prepare for that. 1, here we go. The train traveled m miles at p miles per hour. Okay. It traveled m miles. That's a distance. Distance equals m miles at p miles per hour. Okay, so that's a rate. And we're keeping track of our units in a way that we haven't done in the past. We're going to work on canceling them and making sure that they work out, right? Miles per hour. And it still arrived 1 hour late. So that's what we know about the time, is it was 1 hour late. How fast should the train have traveled to have arrived on time? Oh my goodness. Okay, so what we have to do is we have to use this information first. And what we're trying to do here is we're trying to find the original rate of the train, right? So the original rate of the train is equal to the distance over the time. The time is equal to the distance divided by the rate. We've got both of those. So let's find the time. The time equals the distance, m miles, over the rate, p miles per hour, right? Distance divided by the rate. It's m over p, and now we can simplify these units. So we'll treat them just like a complex fraction. We'll leave the letters b, but we'll multiply this one by hour over miles, and this one by hour over miles, right? We're trying to cancel everything out on the bottom, and we've done that. And now the miles cancel, and so the time equals, I'll write it over here. Time equals m over p miles per hour. I'm gonna write it out so we don't confuse miles with that letter M. Miles, oh, it's just miles. No, it's just hours. Sorry, we canceled out the miles. There's the hour. It's m over p hours, right? So now we can find our rate. Our rate is equal to the distance, m miles, over oh, I see what I'm doing wrong. Never mind. We're not ready to do that yet. All right. Now we've got the time. We've got a distance and a rate and a time for the first scenario. Sorry. Okay. That's what we were trying to do for the first one, is we're trying to find a distance, a rate, and a time. And we did that. We've got everything here right now. Now we're going to flip to the second page. I'm going to copy this so that we've got it. D equals m miles, and the time, the rate equals p miles per hour, and the time we figured out is equal to m over p hours, okay? That's what we figured out in the first scenario. There, I have to straighten up. Now we have our second scenario. And it says, how fast should the train have traveled to have arrived on time? And we knew from before he was 1 hour late. So what we're gonna say is that the time needs to be m over p minus 1 hours, right? We have to subtract 1 in order to get it there on time, right? So now we want to fix this up, just make it a matching fraction. So we'll multiply top and bottom by p over p, right? And then that will become m minus p over p is our new time. Our distance is still, this is hours, and this is m miles. All right, and so to find our rate, which is what the problem asked us to do, we're going to use, this is another version of the same notes, we're going to use this formula that we created, rate equals distance over time. We'll use that to find our new rate. Rate equals distance over time. Our distance is m miles over our time is m minus p over p hours. And then the last thing we need to do is simplify this complex fraction. So we'll multiply this by p over m minus p hours, and then we'll multiply the top by the same thing, right? This cancels out, and our rate is equal to m over p, m times p, I'm sorry, I said that wrong, m times p over m minus p, and that is miles per hour. That's our final answer. That was a little crazy, wasn't it? Finding the time was a little crazy, although not too bad. And then we had to subtract 1 to the time because we wanted to be faster on the second one. And then we used, again, the distance and the time to find the rate. All right? So that's one variation on these. If that felt hard to you, don't worry. It is hard. Let's try another one. And what I'm going to do is I'm going to write up at the top our 3 equations. Distance equals rate times time. Rate equals distance divided by time. And time equals distance divided by rate. All right? Those are not too hard to memorize or to quickly derive, right? The rate and the time both have division. The distance is on the top, and then the other letters on the bottom. All right? So let's try another one. And again, it's a 2-stepper, 28.6. Oh, this is our last one. The boat traveled K miles. Okay, that's a distance equals K miles. In T hours. Time equals T hours. And it was 40 miles short of the goal when the gun went off. So it was 40 miles short. And I'm writing that up here by the distance because 40 miles short is describing a distance. It's not a rate or a time problem. That's going to be an adjusted to my distance. If the skipper tried again, how long would it take to reach the goal if she increased the rate of travel by 10 miles per hour? So this is part 1. And in part 2, what I'm going to do is I'm going to increase the distance. She was 40 miles short, so I'm going to increase the distance to D equals K plus 40. And then I'm also increasing the rate by 10 miles per hour. So that's going to be whatever the rate is plus 10 miles per hour. But I don't know the rate yet, so I have to go back to the first part and find the rate, because that's what's missing up here, right? Well, that's pretty easy because the rate is just the distance over the time. So that would be K over T miles per hour. So now I can write that the rate will be K over T plus 10. Okay, so I've completed step 1 because I've got initial values for D, R, and T. And now I've got a new value for D and a new value for R. And I'm supposed to find the time, right? If the skipper tried again, how long would it take? So my new time will be equal to my new distance, K plus 40, and that's miles, divided by my new rate, which is K over T plus 10, and that's time, so that is, no, I'm sorry, that's a rate, so it's miles per hour. Let me check and see if I screwed that up. This is distance over rate. There's my distance and my rate, right? So that's how I got this. My distance is K plus 40, and that's miles. And my rate is K over T plus 10. Because my old rate was K over T, and we speed it up. We increased it by 10. All right, so now I'm ready to just simplify this kookiness. I have to smush these, and I'm going to have to multiply this by T over T, right? So I'm going to do that the easy, sneaky way, but going like that, right? Then I can multiply this by, I'm going to do it in a different color because it's getting kind of crowded down here, and I want you to be able to see it. T over K plus 10T. This is hours. And this is miles. right? I invert my units as well. John makes a big deal of making sure that your units are tracking along in these. Normally we would just use the letters, but because it's so haphazard, John really stresses that we track the units as well. Hours over K plus 10T miles, right? I've inverted. So now that cancels, hours cancels, miles cancels. Okay, beautiful. Now we just have to clean this up. Up here, the miles cancels to the miles, and nothing else is going to cancel. And our final answer is going to be K plus 40 times T, little baby t. And that will be hours. And then on the denominator, it's over K plus 10T, because that's what I had here, right? This 10 multiplies by that, and then this quantity is on the bottom. This is my final answer, and that is correct. Are you horrified? I think you should be. I am. And I did it to you, all right? Just double checking to make sure we have it right. This looks exactly like John's answer. Beautiful. So let me just recap for you what we did. We start with 2 of the 3 pieces of information. We use these equations to help us find the 3rd piece. This first step is pretty easy. Then what we have to do is look and see what's changing, what John's telling us is changing. Our distance increased, so we took our old distance and added 40 to it. And then our rate changed as well. He said take your old rate, which was here, and add 10 to it. We're going 10 miles per hour faster. Then he asked us to find the time, so we used these equations again, time equals distance over rate. And so then we just used our new value for D and our new value for R, and then we had to do some complex fraction work to sort that out and simplify it. These are really hard problems. These and those babies sucking their formula. I am not kidding you. John is working us hard. So, feel proud of yourself if you understand it even a little bit. Use these examples as you're running across this type of problem in your homework. Feel free to come back and look at your notes, or you can look, they're in the problems are in the book too, right? In the examples that are right at the front of the lessons. So feel free to refer back to those notes as well. Oh, excuse me. I work them just like John does. So give yourself a break. Check. Like what I would do too is when you're working the problem, get this far and then check the solutions manual to make sure that you solved that one correctly. And then maybe again when you look at the changes that you're making, because it's tricky business. Okay, thank you very much. That's the end of lesson 28. You survived, yay! Goodbye.